Dijkstra's algorithm. Dijkstra's algorithm finds the shortest path from one node to the rest in a graph. It works well for weighted graphs, directed and undirected. It is an optimization algorithm, but it is also a minimization algorithm, for it finds the minimum distance path within a graph. Dijkstra's algorithm works only with positive weights, as it fails with negative values. It follows a greedy strategy by selecting the node with the smallest tentative distance. This guarantees the globally optimal shortest path. It has typically a time complexity O of v squared because it needs to iterate over every vertex or node in its simpler implementation. However, it can achieve O of n log n by using a priority queue. Let's see an algorithm example. We will find the single source shortest path from a given node A. Using a table, we will record the distances from node A to the other nodes in the graph. We will also keep track of the unvisited nodes with a list. In the first step, we start visiting the node A, which will be our source node. We record 0 on the table as the distance from node A to itself is 0. The rest of the distances are recorded as infinity since we don't know the distances to those nodes yet. We also mark A in the unvisited nodes list. In the second step, we evaluate which vertices we can visit from our current node A. We can re-edge node B through a weighted edge of 4. We can also re-edge vertex C through an edge with weight of 2. So we update the distances table accordingly. In the third step, we select to visit the node C, as the edge between A to C weighs less than the edge between A to B. We update our unvisited nodes list, marking C as visited. From node C, we can re-edge B, D, and E, so we update the distance table. Note that we always are taking node A as the source or reference for each of the distances in the table, and that we choose always the smallest sum of edges to each of the rest of the nodes. For instance, if we re-edge node B from A, that edge has a weight of 4, but if we re-edge node B, going first through C, then the total sum of the distances A, C, B is 3. So we choose the shortest path because the sum of the edges weight is smaller. Regardless, there are more nodes in between. The distance to node E has two possible paths as well, but again, we take the shortest sum of weights, in this case, the path from A to C and E. The next node to visit is B, since the weight 1 is smaller than 5. Remember to update our unvisited nodes list. From node B, we can re-edge D, so we update our table accordingly. And that's all. Next node to visit is D, since the weight or distances to D is smaller than going from C to E. We update our unvisited nodes list too. And this time, there is no distances to update, as all the distances in the table are already the minimum optimal from the current nodes we are visiting, so we are ready to move forward. The last unvisited node is node E. As we don't have any other choice, we mark it as visited. There are no more updates to our distances list, so we are done. The answer is then contained within our distances table. You can see by yourself each of the listed distances are the smallest with respect to A. Let's take a look to the pseudocode. The principal section of the algorithm are highlighted in red. First, we initialize our distances with a for loop. We set all distances to infinity except the source, which is 0, and set the pref array as undefined for each vertex to track paths later. The prev array will track for each vertex its predecessor vertex in the shortest path. We create a priority queue with all the vertices by keeping the smallest distance vertex first in the queue. While queue is not empty, we pick and remove vertex u with the smallest distances u in the queue. Then, for each neighbor v, we calculate alt, which is a temporary variable, as the distance to u plus the age weight from u to v. If alt is less than dist v, we update this dist v to alt and set the previous vertex to u. Finally, we return the arrays dist with the shortest distances and prev with the previous paths. Here is a Python implementation from our pseudocode. That's all. Thank you for watching.